Okay, I'm going to continue with procedural methods. And I'm going to be looking at an example called the GameOfLife. The reason for this is it's a good demonstration of the use of shaders to do the computation. We looked at Mandelbrot, where all of the work of computing the iterations of the Mandelbrot set were done in the GPU. But the GameOfLife demonstrates another type of simulation in the GPU, where we represent the state of our simulation with a texture. And this means that we can store information from one pass to another by storing that information in a frame buffer, a texture. So let me get a share screen going here. So I'm going to be basically following Chris Wellan's lecture on a GPU approach to Conway's GameOfLife. There are links here to his various programs, and I have followed him pretty closely. So what the GameOfLife is it's a checkerboard universe. It's an example of a cellular automata. The universe is a checkerboard, two-dimensional grid of square cells that have 8 neighbors. And the rules of the GameOfLife are that a cell is either dead or alive, a 1 or a 0. A dead cell, an empty cell, a 0 cell with 3 neighbors in that connected neighborhood of cells around it is born, it comes to life. A live cell with less than 2 neighbors dies of loneliness, and a cell with more than 3 neighbors dies of overpopulation. So here's a famous example of a configuration of the GameOfLife. This is called a glider gun, and it's a sequence of 0 and 1 cells, each following these simple rules of born and die and so forth. It shows examples of gliders, which are little configurations that move continuously across the universe. And you can see some stable configurations, like that little 2 by 2 square that persists until it's hit by the glider gun. So the reason this is really good for a fragment shader is that when we update the cells, we have to have an old copy of the state to which we apply the rules to generate the new copy of the state. So it always requires 2 sets of states, the old one that has the previous generation and the new one that has the next generation. And you can't do it in place because otherwise it doesn't work. It depends on sampling from this older generation. So we're going to use a texture in the GPU to store the state. So each pixel of the texture is going to be 1 cell. We're going to use an RGBA format. Each pixel does have red, green, blue, and alpha channel, but we're not going to actually be drawing this texture. So how this channel is used is kind of unimportant. I'm going to call that the front texture. We're not actually going to be using all the bits, but there are some reasons for using the RGBA. So cells are updated in parallel. The texture can't be modified in place. This would overwrite features that you don't want to be changed until you've updated all of the cells in parallel. So I need a second texture to store this update in, and I'm going to call this the back texture. This is kind of like the double buffering trick that is done automatically. We have a front and a back. We draw it to the back, and then we swap and put that in front. So after the update, this back texture will hold the new simulation state, and we want to swap it into the front so that we can then use it. And here's a little prototype for a swap function that's going to take, it's going to store the front texture, assign it to the back, and then put that front texture into the back for the next iteration. The textures are created in kind of the ordinary way. Here's a prototype for creating a texture. We create the texture, we set its wrap modes and its filters, and we send it to the GPU, in this case with a null, because we don't really care what's in the texture. Using a repeat means that the texture automatically wraps. So things that go off to the right will come back in on the left, which is very convenient for OpenGL. It means you don't have to do special things at a boundary. And our world wraps around. It's a torus, it's a donut. The null there doesn't matter because we're not putting any data in it, so we can leave it blank. It says here that WebGL ensures that it's zeroed. Later, I'm going to access this texture with GL text SubImage 2D that allows you to set individual pixels within our texture. In order for repeat to work in WebGL, texture dimensions have to be powers of 2. So our texture will be a power of 2. So we've played with frame buffers before. We've done GL clear and draw arrays and draw elements. These are all things that go into the default frame buffers. But we're going to have our own frame buffer for holding the back. If a frame buffer is bound at the time of the draw, the output goes into that texture. That texture can then be used as input for another draw command, which is exactly what we'll be doing. So here's a prototype for a step of the function. We're going to bind the frame buffer. We're going to set the texture to be the back texture. We're going to set viewports in that texture. Then we're going to bind to the front texture. And this is a little igloo thing that's going to draw our triangle strip, which is basically just the 4 corners of our world. And then I'm going to swap it. So we're binding to the custom frame buffer that we created somewhere before, no initial configuration. The back texture is attached. This will replace any texture that is currently there, like the front texture, and we set the size. This thing, Igloo, this is a pointer to a whole thing about Igloo, including a download or the GitHub to get this stuff. Igloo is a Yappy, yet another API, similar to 3JS, but completely different. But this is going to draw this will make our shader run on the little quad that we're drawing in our texture. It doesn't actually matter what the quad is because we're manipulating the pixels and not the quad itself. The simulation rules are all in the fragment. So the JavaScript's real job is to just basically draw the arrays, this quad that we're drawing, over and over again. And all the rules will be in the fragment shader. So here's the GameOfLife fragment shader. We have a sampler of the state. That's looking at the previous generation. That's our buffer. We have a little function here, get, that's going to sample that texture at the fragment coordinate plus this X and Y offset that we're looking at. And this is also, I'm only actually looking at the red channel. And then here are the rules of the GameOfLife. The get function is going to add up the sampling of the texture at the upper row above our cell, the lower row below our cell, and the cell to the right and to the left of our center, to the right and to the left of our center. And here are the rules. If the sum is 3, then it's born. If the sum is 2, if the sum is 2, it survives. If the sum is less than 2, it dies. So, and I mentioned this get function returns the value of the cell at X and Y, 0 or 1. We're only looking at the red channel. There are 3 other channels that aren't being used. And because loops are expensive in GLSL, all of this is unrolled. So it's not using looping, even though you could. So we need to be able to see this simulation. So we have a prototype for drawing. In this case, we'll render the simulation state to the default frame buffer. So I bind to the frame buffer, set its viewports, bind the texture to the front, and then here's that little igloo fragment where we're drawing our quad with the triangle strip. So it bound it. We could use the null as the default. We set the viewport and copied the state into the frame buffer. And since pixels are really small, there is a scaling here to make it a little bit bigger, 4 times bigger. And here's what the copy shader looks like. So we're using one shader to do the state. We're using another shader to draw that state. So this just sets the fragment color to the texture to a sampling of that state at the fragment's XY positions divided by that scale. This does mean that the shader runs 16 times per cell since I'm scaling it by 4. I'm using GL nearest on the texture, so that doesn't really matter. It's just going to sample the pixel that's nearest to those 16 calls. If you'd use GL linear, it would be blurry. The frag coordinate is in window coordinates, so I need unit coordinates between 0 and 1. And that's why I'm dividing the frag coordinates by the size of the viewport. Alternatively, you could pass the coordinates as a varying that would be automatically interpolated. It's important to note that the simulation state never leaves the GPU. It's updated there and it's drawn there. The GPU is operating the whole simulation like a marionette. For the simulation to be interesting, we need to be able to put cells into it. And so here's where GL text SubImage comes in. It's used to set the values of some portion of the texture. And the poke method does this. When we poke it, which will be a mouse click, it's going to set a value at X and Y. It binds to the front texture, and here it uses the SubImage on that texture to put a 255, that's the value V, in the RGB coordinates of my RGB. So that way we can poke the simulation and put cells into it. I added a little option to Chris's program that initiates what's called the LRPentangle state. This is an example of a Methuselah, an initial state that persists for a really long time. It doesn't settle down. It's similar to the glider gun, but the glider gun is kind of just shooting out those gliders. This one I'll show you in a second. And here all we're doing is putting ones in a little array that looks like this. There's 3 in a row, there's 1 up in the middle, and there's 1 down at the end. Sometimes you might want to save the state. There are a number of different ways you could do it. You could grab a rendering of the simulation and translate it back. You could take a screenshot. That's even messier. The way to do it is with read pixels on the frame buffer. We can read the pixels out of the frame buffer. Here's the get function that reads out of the step frame buffer, the texture front. It makes an RGB of the appropriate size, reads all the pixels from that from the frame buffer, and it returns that. So RGB is passed back to the SubImage 2D as a snapshot. Chris says that the project was simpler than he anticipated. He also did some liquid simulation using a similar technique. Because this is run in the GPU, it's really, really fast. He says he gets 18,000 iterations per second if he doesn't bother to draw it. But as you'll see, the things settle down pretty quickly. Let me show you the program. Here's Chris's GameOfLife with my minor modification so that there's an LRPentangle. It starts with a random array. We can stop and start it with the space key. We can clear the simulation with the delete key. We can poke it by running the mouse over. You'll see these things kind of settle down pretty quickly, and the L key clears the screen and sets, let me stop it, the L key sets up that little LRPentangle, which I'll let you play with, and you can see that it runs for a long, long time before it ever settles down. There are a number of steady states that you can see that appear in here, the little squares, these little diamond shapes that settle down. Spinners are little ones 3 in a row that alternate back and forth between an up cross and a down cross. And of course, our gliders that slide across the world all the time. So have fun with that, have a look at it. This is an example of a multi-pass shader where we're using textures to store the state of the simulation. Later, I'll try and do an n-body problem where we actually calculate a bunch of physics with a multi-texture, multi-pass shader. So I'll stop that. I'll stop the share screen, and I'll end the recording. I'll see you all in class. Bye.